All right, take it away, Ethan.
All right. Hi, everyone. So today I want to talk about how we can use tracking data to create better measures of defensive skill and how we could use that to inform better defensive alignments. So right now, defensive alignments are mainly built on the spray angle of the hitter, and that's probably valid. That's probably where most of the advantage in shifting comes from, if you were to just look at that data. And we see that over time, the shift has increased over the past, let's say, 10 years or so, or a little less than 10 years, and that BABIP and WOBA have also steadily decreased on ground balls. And we see on the left, we see Rockies and Cubs game. It's the infield shifted against Chris Bryant a little bit to the left. It looks like the second baseman's playing one step, maybe two steps towards second base. So to kind of show the motivation for this project, here's a kind of experiment to establish that different combinations of defender skills would yield different optimal alignments. So if we see the black dots, if we treat those as the 50th percentile positioning that an infield would take against a hitter, where would a third baseman who's below average on plays to his right stand relative to the black dot? Well, I think the third baseman would move, if they're below average on plays to the right, they would play a little bit more towards the line. And if they're above average, they might play a little more off the line. So now that we've established that tracking data, better measures of defensive skill could inform better alignments, here's how tracking data can enable better skill evaluation. So right now, one of the best metrics is outs above average. It uses tracking data. It uses the probability of an out to determine credit or no credit. And it considers those 4 factors. And it allows us to say things like player X is 50% better than player Y because he makes 15 outs above average and player Y makes 10. That's great. How does it inform better defensive alignments? Well, the main problem with the current construction of defensive metrics like outs above average is that it's cumulative, first of all. How did you get there? 100 routine plays as opposed to 10 difficult plays. And it can't be proactively applied for strategic decisions regarding shifts, or if it can, it's not come to me yet. So how would you interpret someone who has a plus 12 arm value on their left if they're the starting third baseman? Your starting shortstop has minus 10 arm value, and your shortstop to the right, or your backup shortstop has plus 10 arm value, and these are to the right. You know, this is a real metric. We can calculate arm value left to right, directional, outs above average, all these different flavors of defensive metrics. But how do you translate 12 arm value and minus 10 and plus 10 into an alignment, right? We want our starting shortstop probably to play a little more to the right, but we want our backup shortstop to play a little more to the left. It's like, where do we know where to put these defenders? We can't do it rigorously. So in order to kind of solve that problem, my project kind of looks at the time for a ground ball to be an out, hypothetically. And so what you need in order for this project to kind of work is a given exit velocity and a defensive alignment. So we could say the black dots. So we need an exit velocity. From each defender's starting position, and this is the process for how I determine the range, for each defender's starting position, increase the distance by 1 foot to the left or right perpendicular to home plate. So these lines are perpendicular to home plate, and I'll go into them more. At that point, determine if they could reach the ball, because through this perpendicular process, we're able to tell where the ball is at the perpendicular point and say, okay, it's 115 feet away from home, so we know how far it is from home. If they can reach the ball, determine if they can make the out. I'll go into that. And then repeat until they cannot make an out. So through this process, this perpendicular process is what I say throughout the presentation, you're able to create these range limits. And so we see here, it's a little hard to see, but there's a red and a green. And the green extends a little farther because that's a 75th percentile shortstop or third baseman, and the black is 25th percentile. And the other advantage of this is not only that we can inform better alignments, but that we can find the X BABIP or X WOBA of any alignment, and I'll go into that as well. So I want to introduce an idea that ground balls are a series of races. It's not that new, but ground balls are a series of races between defenders and the runner. So if the defender can reach the ball, transfer it, throw it, all in the time it takes for a runner to reach first base, they get the out. So there's two kind of races that are involved in this project, the ball defender intercept race and the defender hitter general race. So the first race is about, can the defender beat the ball to the spot that's perpendicular to them X feet away from their starting position? If they can, how long did it take? So there's two kind of components to that. There's a ball component about how long it takes a ball to reach a certain point on the field, and then a defender component, which is used based on their skills. And if the ball component's equal to the defender component, then this first race is equal to the ball component. Race 2 is just the general race that I was talking about earlier. It's the time to reach the ball, time to transfer, and time to throw, and then it's based on the runner's speed. Or hypothetically, it'd be based on the runner's sprint speed, but here I just used average sprint speed everywhere. But that's an easy modification. So here we see the defender component and the ball component of the first race. So ideally, on the defender component, right, we'd want to use defensive plays in order to look at their movement skills. But there's just not enough data. I think people talked about there's 97 games, and surprisingly, that's just not enough data to say, what is your maximum left-right movement skill? So I have to use the sprint speeds to 0 through 90 feet on plays where any given defender was actually the hitter. So we're kind of translating between situations, and there's going to be some error involved with that, but I just had to for this project. The ball component uses ball bounce data, which were labeled events in the data, exit velocity, and distance from home, to model how long it would take a ball, again, to reach X feet away from a defender through the perpendicular process. So I also built two other models, KNN and bag trees. They performed really similarly. The MAEs were within like a hundredths of a second, or hundredths of a millisecond. And we see that on the right, the mean average error of the linear regression was 154 milliseconds based on the ball bounce data, exit velocity, and distance from home. Next, we have the transfer time and throw time. And the transfer time was easy. It was just the player's best transfer time at any or throughout the data set. And then the throw time model I used similarly to the last linear regression or to the last model, the initial velocity, the distance, and we're able to say how long will a throw take to first base, given, importantly, a defender's best throwing velocity in the data. So with all the components kind of built up, we can test some ranges. And I chose to use Patrick Wisdom's batted ball profiles as a kind of illustrative example. Again, if you remember to the beginning, the only thing we need in this project is the initial exit velocity of the batted ball and an alignment in order to get started. So we input a base alignment, say it's the black dots that we've been used to, and then we enter the player-specific data to the models and compare the times at these perpendicular 1 foot distances. And so the results of combining all the components of this project are that we see within this data, importantly within this data, the max range of third baseman is 12 feet on, and it seems really specific, on 91.2 mile per hour exit velocity ground balls, and that's just because it's Patrick Wisdom's data. It could be anybody's. The 75th percentile third baseman can make 17-foot plays away from the starting position, and at each point along that 0 through 17 feet, he makes the play at around 450 milliseconds faster than the 25th percentile. And then on the bottom, we see the shortstop data, the results, and we see 21 versus 25 feet, 350 milliseconds around that, and we also see that on the graphs, all the lines are increasing linearly. It looks like that just because the models were linear regression models. So as a result of all of this process, we're able to, again, input a defensive alignment, input an exit velocity, and we could build these alignments. And so we have on the screen 5 different figures, and the red is, again, the 25th percentile, green is 75th percentile, and we see the differences in ranges. And in the bottom right, we see the beginning graphic where it overlays good and bad. And we see there's some difference in terms of their max range, and it's not on the screen, but there's also a time difference. Okay, so this is where I think this project could be important. So using spray angle, exit velocity, and WOBA data, we could establish the X-WOBA, a different construction of X-WOBA, on any alignment and any X-BABIP. So if we know the probability that a hitter will hit it to any point on the field, like the angle, and we also know the probability of, at that point, the ball being hit at a certain exit velocity, we could iteratively test different alignments and say, will the fielder make an out on this ball or this ball, and test all different kinds of alignments and say, what's the X-BABIP? We can also do the same thing with WOBA, if we, again, kind of condition on a point on the field and say, what is the X-WOBA data of this alignment? Will they make an out? What's the probability they'll make an out? What's the distribution of WOBAs at that point? And we're able to say, X-WOBA of any alignment. So this has some pretty concrete applications, I think. I think that you could automatically test alignments before every game. You could have it automatically try to find some good alignments, or maybe test some new ideas you're thinking about. And I think possibly there could be interesting findings from that. Maybe there'd be some very strange alignments. Maybe not, too. Probably not, actually. But more specific skill evaluation is needed, and more realistic models of the defender path on the ground balls are needed in order to make this project even better. So right here we see on a graph, on a table, we see that there could be huge differences between players going to their left or their right. 17 points of absolute difference for Alcides Escobar is the difference between a very good shortstop and a very average one. So there's a lot of meat still to be picked on this bone. If we're able to split the movement ability on a left-right basis, we could say, okay, he could actually make plays 21 feet to his right, but 23 feet to his left because the throw is easier and the transfer might be easier. The perpendicular path that I kind of harped on here, it could be modified. I think we could, instead of going perpendicularly, once we reach the limit at the perpendicular point, start moving 1 foot back iteratively and doing the same process. And I think another better improvement would be better tracking data, but this project opened up so many new realizations about the potential of different types of data, and I'm really grateful to SMT for providing that and this opportunity. So yeah, that's it.
All right, thank you, Ethan. You can tell he has CMU influence on him because he complained about wanting more data. Very good, very good. All right, well, we have time for a couple questions. Hand over the mic to Kwong. Raise your hand if you have any questions.
Oh yeah, sorry.
Any questions?
Hi, yeah, it's a really nice talk. I'm just a little bit curious about regarding third baseman or shortstop. Have you looked into the how their awareness, like before the ball was hit, where they predict the ball is going to fly to, that whether that's contribute to better defensive stat, or it's just no relationship between this kind of awareness and the stats.
So are you talking about like their own like decisions on the field before the ball is hit about where they might want to play?
Yes.
I haven't looked into that because I would imagine that defenders generally want to just play where, and I don't like to say it, like where people tell them to play, maybe, but I didn't look into that, no.
Okay, thank you.
All right, we have a question in Steinberg, and then we're going to switch over to the poster previews. The boys.
Hi, thanks. Great talk. Related to the previous question, how would you consider trying to sell this to either a player or a coach in terms of either a graphic or a talking point where you could say, if you took 2 steps to the right, you'd get so many more outs per game. Have you put any thought into the communication part?
Not too much, but I would say that, yeah, marketing it in terms of, outs could be nice, runs, all those types of things. I think you could also use like other different types of like data, maybe like X-WOBA data in order to make it even better. But yeah, I think marketing it in terms of like outs and runs and concrete results would be my, point number 1.
All right, let's thank Ethan.